Yeah, so let me start by thanking the organizers for organizing this event and for giving me the opportunity to speak. So yes, I'm a PhD student of Marius Krijnik in Utrecht. And so far, the main focus of my PhD has been the study of momentum maps. So today, I want to tell you about stratification of the transverse momentum map. So let me first introduce what I mean by the transverse momentum map. And to start with, let me recall the definition of a Hamiltonian G space or Hamiltonian action. So let G be a Lie group with a Lie algebra map frag G. And let S omega be a symplectic manifold. Then by a symplectic action of a Lie group G on the manifold, a symplectic action of the Lie group G on the symplectic manifold is called Hamiltonian if there is a G equivariant momentum map. So this is a map from the symplectic manifold into the dual of the Lie algebra, and it's required to satisfy a so-called momentum map condition, which I think is probably easiest to understand in a diagram, right? So given any action, we have an induced infinitesimal action, which is a Lie algebra map from the Lie algebra to the Lie algebra vector fields on the manifold S. And if the action is symplectic, then this infinitesimal action, it actually takes values in the symplectic vector fields. Now, requiring the action to be Hamiltonian, this infinitesimal action actually takes values in the Hamiltonian vector fields on the symplectic manifold. And Hamiltonian generating this vector field, it's assigned by the momentum map. So it's the function obtained by applying the Xi to the momentum map to Xi. All right, and now the transverse momentum map is the map induced by the momentum map on the level of orbit spaces. So by equivariance of the momentum map, it descends to a map between the orbit spaces. And this is what I mean by the transverse momentum map. All right. Now, the first problem when studying this map is that its domain and its codomain are in general rather singular. So to make these singularities a bit more well-behaved, throughout the rest of the talk, I will assume that G is a compact Lie group. So this means that, well, these spaces are still singular, but now they are naturally stratified by smooth manifolds, right? And these stratifications, they are naturally associated to the actions. However, they need not be compatible with the transverse momentum map. So this is a problem. And the first or main aim of this talk is to introduce stratifications of these orbit spaces that are compatible with the transverse momentum map. And then at the very end of the talk, I want to discuss the Poisson geometric properties of these stratifications, but that's only at the very end. Yeah, so before I turn to the details, maybe a short remark is that the spaces that the Hamiltonian actions that I usually study, they are of a more general class, namely actions of proper symplectic groupoids. And well, the main theorems of the talk today, they actually hold in this generality. But for this talk, I will just restrict to Hamiltonian Lie group actions. All right, so let me start from the beginning by saying what I mean by stratification. So throughout the talk, X will be a topological space, which we assume to be Hausdorff, second countable, and paracompact. Right? Now, by stratification of such a topological space, we mean, first of all, a partition of the space into smooth manifolds. And well, these manifolds, which we call the strata of the stratification, they are required to satisfy some conditions. So first of all, they should be locally closed inside X. Secondly, so they're given, well, yeah, the stratification, so these strata, they're given a topology with respect to which they're manifolds, and this should be the subspace topology in X. And what's important is that we assume this to be connected. So this is not always assumed everywhere, but we do. And then the third condition is the so-called frontier condition, which is saying that the closure of each stratum is a union of the stratum with other strata of strictly lower dimension. All right. So
excuse me, do you assume your stratification to be locally finite?
Oh, sorry. Yes, that's missing. Yes, that's a good point. Thank you. Yes, of course. All right. So one source of examples comes from real algebraic geometry, more generally from semi-algebraic subsets over N. So each such subset admits a canonical stratification. So let's consider an example. Let's consider the algebraic set given here. So this is well, drawn in this picture here, and we can stratify this. So it looks a bit like an umbrella. It's called the Whitney umbrella, and we can stratify this in the following way. So it has two dimensional strata, two one-dimensional strata, and one zero-dimensional stratum, namely the origin. Now, of course, if we would just want a partition of this set into smooth manifolds or smooth submanifolds of R3, we could have also taken the right and the left two-dimensional stratum and just the whole z-axis. However, this would not have satisfied the frontier condition, right? Because the whole z-axis, it's not contained in the closure of either of these strata. Right? This is just to illustrate a bit the conditions. And well, the main source of examples in this talk will be coming from orbit spaces of compact Lie group actions. So I'll define in a minute. I'll define more explicitly how the orbit space of a compact Lie group action can be stratified. But for now, it may be good to give you already an example in which it's somehow clear what the stratification should be. So consider the action of S1 by rotation on the z-axis on the 2-sphere. Then the orbit space will be a closed interval, essentially given by the height. This is, of course, can be stratified by taking the interior and the two endpoints. All right. So before I turn to the explicit description of the canonical stratification associated to a G action, I think it's good to recall a bit the linearization of such actions. So let's consider a G space M, a point X in M and an orbit through X. Then the normal bundle to the orbit is canonically a G vector bundle, where the action is given essentially by, well, every element in the group. It gives you a diffeomorphism of M. Differentiating this gives you an isomorphism of the tangent bundle to itself. And this descends to a vector bundle map on the normal, vector bundle automorphism of the normal bundle. So this gives an action. And this action is linear in the fiber directions, right? So the linearization theorem for G actions says that there exists a G equivariant tubular neighborhood of the orbit in M. Now, so this can be thought of as a local model for the action. This local model, it can actually be built out of simpler data, namely that of a Lie group and a representation of the group. So the Lie group is the isotropy group at X, consisting of all elements that fix X. And well, elements that fix X also fix the fiber over X of the normal bundle, and therefore they act on this fiber to give a representation of this group. And this is, well, I'll call this the normal representation at X. And as I said, the local model can be recovered from this because as a G vector bundle, the normal bundle is isomorphic to the associated vector bundle. All right. So the takeaway here is that the local model around an orbit, it's essentially encoded by this representation here. So now let me give you an explicit description of the stratification on the orbit space. So the general procedure here is that there are various natural stratification partitions of the orbit space to consider, and they will give you partitions into manifolds. However, the members of the partition may not be connected. Usually they are not, but after we take connected components of their members, they all give the same partition, and this is actually a stratification of the orbit space, and this is what we call the canonical stratification, denoted by SG. So the first such and the simplest such partition we can consider is given by the equivalence relation written here. So two orbits, an orbit through X and an orbit through point Y, are equivalent if and only if the isotropy at X is isomorphic as a Lie group to the isotropy at Y. All right, so this defines a partition which we call the partition of by isomorphism types. So another partition that we can consider is defined as follows. So two orbits are equivalent if and only if there is a G in the group such that the isotropy at X is G conjugate to the isotropy at Y. I think this is the most well-known partition inducing the canonical stratification, which sometimes or often is also called just the orbit type stratification. Right, and the final partition that I want to tell you about is the one by local types. So here two orbits are called equivalent if there is a G in G such that the isotropy is G conjugate to the isotropy at Y. But now we also assume that there is a compatible isomorphism between the normal representations at the 2 points, where compatible, of course, refers to being compatible with the actions. All right, so this defines a partition called the partition by local types. And the name here comes exactly from what I told you a slide before, namely that this condition really means that this is equivalent to saying that the normal bundles to the orbits are isomorphic as G vector bundles. So this is really saying that around these orbits, the G space locally, it looks the same. Therefore, local types. All right, and so, well, these are three different partitions. One is finer than the other. But as I said, after taking connected components, they give the same stratification, and therefore they all tell you something about the stratification. So this one is somewhat easiest to compute, but this gives you the most information somehow. All right, now let me turn to the first main theorem of the talk, which is the following. So we're given again a Hamiltonian G space with G a compact Lie group. Then the theorem is that the transverse momentum map, it admits a canonical constant rank stratification. So what I mean by this is, in general, if we're given two topological spaces with the same topological properties as before, and we're given a continuous map between these spaces, then by a constant rank stratification of the map, I mean, first of all, stratification of the domain, secondly, a stratification of the codomain, and this should be compatible with the map F, first of all, in the sense that F maps each stratum on X into a single stratum in Y. So this is the first condition here. Secondly, well, these are manifolds, so we want to require that the restriction of F to the strata is smooth. And finally, we want to require that F has constant rank and restricted to the strata. So this is really a condition on the singularities of the map somehow. All right. So now let me be a bit more precise, because it turns out that to construct such a stratification of the transverse momentum map, we can, first of all, we can take the stratification by orbit types on G star mod G. And all we have to do is really find the refinement of the stratification by orbit types of S mod G. So the statement really is that there is a natural stratification, S-Ham, which I call the canonical Hamiltonian stratification, with the property that together with the orbit type stratification on G star mod G, it forms a constant rank stratification of the transverse momentum map. And secondly, well, as I said, it refines the orbit type stratification SG on S mod G. So let me give you an example where it becomes clear that we really have to refine the orbit type stratification to achieve such a, to find such a constant rank stratification of the transverse momentum map. So take G to be the special orthogonal group. Then the duo of the Lie algebra can be identified with R3 in such a way that the co-joint representation becomes just a standard representation of SO3, so just acting by matrices on vectors in R3. So this has two types of orbits, namely the origin, and the other types are the concentric spheres. These are the orbits. And so the orbit space, it can be identified with the positive or non-negative real numbers. Now we can take the, as a symplectic manifold, the cotangent bundle of G and consider the cotangent lift of the G action on itself. So this is a Hamiltonian action. And well, first of all, this has the property that the orbit space S mod G is, well, the action is free. So in fact, the orbit space is smooth and is diffeomorphic to the duo of the Lie algebra. And under this diffeomorphism, the transverse momentum map, it becomes identified with, well, the norm squared. All right, now here we see that since the action is free, the orbit type stratification of R3 is just consists of one stratum, it's just the manifold R3. Whereas the orbit type stratification of G star mod G, it consists of two strata, namely the origin and the strictly positive real numbers. Of course, since this map is surjective, it can never map this stratum into a single stratum here. So in this case, the canonical Hamiltonian stratification would rather be, it consists of two strata, namely the origin and the rest. Right. So as for the stratification associated to a G action, we can give a similar type of description, explicit description of the canonical Hamiltonian stratification. This is in fact how one constructs it. Right, so first of all, there is an analog of the partition by isomorphism types, which I call the partition by J isomorphism types, which is saying that two orbits in S through a point P and through a point Q, they are equivalent if, first of all, the isotropic groups of the action are isomorphic. But then we also require that the isotropic groups at the image points under the moment map, they're also isomorphic. So these are the isotropic groups of the co-joint action. All right, so this defines the partition by J isomorphism types. And basically by definition, we can, well, its members are given by subset of the following form. They are intersections of orbit types isomorphism types in S mod G, intersected with the preimages of isomorphism types in G star mod G under the transverse momentum map. All right, so for the orbit types, we can play somehow the same game or similar game. So the J orbit types would be defined by saying the two orbits are equivalent if and only if there is a G in the group such that, first of all, the isotropy at P of the action at P is G conjugate to that at Q. And secondly, we require the same for the isotropy groups at the image points under J. And then finally, we can give an analog of the partition by J local types, which I call the partition by J local types. And so in short, what we do here is replace the normal representations or the normal bundle by the symplectic normal representations. So this is, as a symplectic vector space, it's the fiber of the symplectic normal bundle to the orbit. And this is canonically a representation of the isotropic group. Yeah, so explicitly, well, the equivalence relation is written here explicitly, but think I said it all. And as before, one can give a more geometric interpretation of when two such orbits are equivalent in terms of a local model for the momentum map, right? Saying that around two such orbits, the momentum map, it looks the same. But I will not go into detail about this now. Rather, I would like to discuss finally the Poisson geometric properties of this stratification. So to give you some context here, first let me recall a bit about Poisson and symplectic reduction, basically. So somehow the simplest, well, first of all, even though this space it is singular, there is a natural candidate for the algebra of smooth functions on this space, namely the G invariant smooth functions on S, which of course descend to actual functions on the orbit space. And well, the first thing one may note is that because the action is symplectic, this algebra, it is in fact a Poisson subalgebra of the Poisson algebra of smooth functions on S with the Poisson bracket coming from the symplectic form. Right, so this is, I guess, the simplest version and purely algebraic version of what one could call Poisson reduction. Then there is symplectic reduction, which in the singular case is due to Lerman and Chamard. So this says that the symplectic reduced spaces over each coadjoint orbit O, which, well, are as sets, they are the fibers of the transverse momentum map. So these are singular spaces, but they can be stratified in a natural way. And in fact, the strata have a natural symplectic structure. So they are symplectic stratified spaces. So of course, when the action is free, this is just the usual Marston, Weinstein, Meyer symplectic reduction. All right. Now, so there is somehow a more geometric interpretation of this Poisson structure here on the orbit space. So geometrically, this bracket or this Poisson structure is reflected in Poisson structures on the orbit types of the orbit space. So more precisely, each stratum of the orbit type stratification on S mod G, it is a Poisson submanifold of the orbit space equipped with this reduced Poisson bracket. So here submanifold has a precise meaning, but let's ignore this for now. So what you should read here is that it has a natural Poisson structure induced by by this bracket here, right? And this is an actual Poisson structure on an actual smooth manifold, so it has symplectic leaves. And these are the symplectic strata given here. So this is all known. And now, well, essentially what I want to add to this is that is the role of the canonical Hamiltonian strata in this picture. So first of all, as for the orbit type strata, they are Poisson submanifolds of this orbit space with its reduced Poisson bracket. But they are regular. So this is really what distinguishes them from the orbit type strata. So they are regular Poisson submanifolds, meaning that the Poisson structure, the symplectic leaves on these Poisson manifolds are of constant rank, right? And as before, we can give a more explicit description of the symplectic leaves. So as before, they are, well, let me start with point 2. As before, they are the symplectic strata of the symplectic reduced space. But now we can also see them really as the fibers of this constant rank, or the connected components of the fibers of this constant rank map, which we obtain by restricting the transverse momentum map to the stratum here. So this is really a constant rank map. Therefore, its fibers, they foliate sigma, and this foliation coincides with the foliation by symplectic leaves. So yeah, with this, in this picture, one can really see the reduced spaces as stratified spaces as the fibers of this stratified map. All right, that's all I wanted to say. Thank you.